Physics is written in a very precise language called mathematics, and we need to be automatic with our ability to use the math we need in this course. That helps us free up our thinking for more challenging scenarios and thinking through a lot of the concepts in physics when solving problems. So let's make sure we, at the very start here, understand what is meant by scalars, vectors, and then doing some simple one-dimensional vector math. So it's worth your time to really master these things at the beginning. A couple instances of scalars here I've put down. So time is a scalar. It doesn't have a direction associated with it, just a magnitude. And mass is a scalar as well. No direction associated with mass. That's in contrast to some vectors that you see over here I've drawn. Here's a vector that's 2 meters in length, and it's pointing to the right, and then this one is pointing down, and it's pointing in the negative direction, and it has a length of 3 meters. Also using the symbol X for a horizontal vector and the symbol Y for a vertical vector, standard to do in physics. So we start with scalars, and those are quantities that just have magnitude or size. So things like time, volume, mass, temperature, speed, distance. No direction associated with these things at all, but varying sizes of the quantity. A lot of times in physics also we'll just say time. To be more specific, we should say clock reading, what's the instantaneous reading on a clock, or time interval. But sometimes we'll just say time for brevity when we're talking about an instantaneous time quantity. The nice things about scalars is that they follow the simple math rules of addition, subtraction that you know. All right, so there's really nothing new to learn in terms of math rules for scalars. However, the new mathematical object that we're building up now are called vectors, and they have both magnitude or size and direction associated with them. And some examples there, we in our previous video learned about the position vector, but we also see things such as displacement, velocity, acceleration, force, momentum. Maybe you've heard of some of these words before in the everyday speech. They have precise meanings in physics that we're going to be building up, and all of these quantities are vector quantities. They have direction associated with them. And because they have that extra little bit called direction, that makes them a little bit more complex mathematically. And we have to develop these new mathematical rules to add, subtract, multiply, etc. These things called vectors. And we're going to build that up here for just one-dimensional vectors today. The first thing to note about vectors is that they remain unchanged as long as their magnitudes and direction don't change. So for example, I've just drawn some vector. I'm calling it vector A. Remember, this half arrow is the notation we use above the variable to denote that it's a vector quantity. And here is the vector as drawn by that arrow. And I could literally grab it and move it over here. I can move it anywhere in the plane I wanted to, and as long as I don't change the direction or the magnitude, it's the same mathematical object. So over here now, it has not changed. It's just on a different space and in the two-dimensional plane of the paper here. I'll bring it back over here. All right, so that's kind of the first idea, that you can move a vector around in the plane or even in three-dimensional space as long as you don't change its magnitude and direction. Next, let's build up the very important vector math operations, and there's going to be 3 of them here. We'll start with scalar multiplication, and I'm going to show you how you can draw little pictures for scalar multiplication. That's called a graphical representation. And then we'll also do scalar multiplication in symbols, so you can see how that same idea is expressed mathematically in symbols and equations, etc. All right. So the idea is a very easy idea. Let's say we have some vector A, and I'll just draw that in the plane here. Okay. And then I have a simple question for you. What if we then had 3 times as much A? What would the vector look like if you had not A, but 3A? Pause the video and try to draw it. So hopefully pretty intuitive for you. You should have drawn an arrow like this. That was about 3 times, or exactly 3 times as long, and pointing in the same direction as vector A. Now, how does that show up in a graphical way? Well, it would look something like this. You just take A and you add on another one, and then you add on another one. So here we have A, and A, and you add those 3 together and you produce a new vector that is 3 times as long. You could give that a name if you wanted to. For example, down here in symbols, we could say there's some new vector c, write that again, some new vector c that is 3 times vector A. And so this is called scalar multiplication because the number here 3 is a scalar. It's just a magnitude. And what it's doing is it's stretching the vector. It's either expanding it out or contracting it. Maybe another vector we could do would be something like this. Maybe we construct a new vector called b, and vector b is 1/2 of vector A. So what would that look like? Well, it would just be a vector that's half as large as vector A. So this would now be vector B. That's all scalar multiplication is. A key idea is that it does not change directions. I'll even write that here. It does not change the direction of the vector. Just the size or just the magnitude. Very important point. All right, so let's take a look at vector addition. Very important mathematical skill to master, and it's pretty easy. What we do is we do what's called the tail to tip method. So let me show you how to do that. We've got vector A here. It has a magnitude of 3. I've just written that above each vector. And then vector B, and it has a magnitude of A. And what we're after is adding the two together. So in symbols, that would be we're trying to figure out what is A plus B. And we could call that vector some resultant vector. So the addition of these two vectors A and B is going to create a new vector that I'm calling vector R for whatever reason. Usually that's done to call that the resultant vector when you're just kind of abstractly doing this in a general math way. All right, so how do we do the tail to tip method to add these two vectors? Well, first thing is look at the addition, draw the first vector. So draw A. All right, so there it is right here. There's vector A. And then what we do is we take the tail of vector B, which is right here, and we place that onto the tip of vector A, which would be right there. Essentially, we're kind of superimposing vector B at the end of vector A. So let's do that. Something like that. All right. I think I drew B a little bit too long. Do that again. And you want to try as best you can to get the sizes when you're drawing them exactly correct. All right, perfect. So we've taken the tail of vector B, placed it on the tip of vector A, and then what we do is we draw a straight line from where we started our drawing, which is right here, and we draw a straight line to where we stopped our drawing, which was right there. So from start to finish, and usually I put a little dot where we started. So start and then finish, and that's it. And then to figure out the magnitude of this vector that has been constructed, we could take out a ruler and measure it according to some scale that we have previously set up to measure these other two vectors. That's one way to do it. Or we could learn just some simple symbolic operations that we'll see now. And in the case of one-dimensional vectors, what's really nice is if you want to add them together, you can just add their magnitudes together. So for example, we can come along here and to find the magnitude of the resultant vector, we just add 3 plus 1. So we have 3 and then 1 there, and we can do that very easily. So that would give us a magnitude of 4. Now, I don't even want to write that out in a general formula right now, because when you do this in 2 dimensions, things get a little weird, and I'll give you a sense of that right now. So take a look at what I've done. Look at what I've done to vector B. I haven't changed its magnitude. It's still equal to 1. The size is the same, but I rotated it. Now vector B is pointing vertically up instead of horizontally to the right. So this would be a problem of vector addition in 2 dimensions. And I'm kind of showing you this now because it is an important idea to see something special about vector addition and just how it's different from regular addition with numbers, right? Over here it seemed pretty easy. Okay, 3 plus 1 is 4. Got it. Nothing new to learn, but you got to watch out because when you're adding vectors now in 2 dimensions, it's a little trickier. So follow the same rule. we start here at the beginning where we started our drawing, so vector A. We took the tip, we took the tail of vector B, and we added, or this vector B, sorry, we took the tail of vector B and we put that onto the tip of vector A, and now we just draw a straight line from where we started to where we finished, so something like this. Just following that exact same procedure. And I hope you can realize that this length right here is absolutely not equal to 4. I'd like you to pause the video and see if you can figure out the magnitude of this vector now when we add A and B together. Go ahead, try it. So I've worked it out here. And hopefully you saw this is just a right triangle. And you can use the Pythagorean theorem. So you would do 3 squared plus 1 squared and then the radical. And that would give you square root of 10 or 3.16 as shown here. So the magnitude of this resultant vector now is not 4 at all. It's not 3 plus 1. It's 3.16. So in general with vectors, you absolutely cannot just add the magnitudes of vectors and think you're going to get the correct magnitude of the resultant vector. Now it will work in one dimension. That's the only time that's going to work here. You're taking the magnitude of the first vector 3 and adding to that the magnitude of the next vector 1 and producing the right answer, number 4. But that's a very special case where it just happens to work out in one dimension. In 2 dimensions, that will not work. In 3 dimensions, it won't work. So we're not even going to write down some rule that says that you can just add magnitudes like that. In general, you can't. Okay, you got to work it out like we've done here. Now I'll challenge you a little more. What if we just took vector B and instead of having a point straight up, what if we pointed it back kind of like at this angle? I'm not even really specifying what angle that is right now. But how would you add these two? So try that with the graphical method. Hopefully you can now see how to do this. So pause the video and add these two vectors, and then just look at the picture you've drawn and think about, how would I calculate the magnitude of the resultant vector now, the size of the resultant vector? Okay, pause the video and try that. Okay, so I've done the tail to tip method. I drew vector A, then I put the tail of vector B on the tip of vector A, and now I'll go from where I began. I started, and I'll draw a straight line and finish it off with the tip of an arrow where I finished, just like that. So here's my start point, here's where I finished, and now that line would represent the resultant vector, and we could measure its length with a ruler if we wanted to, with some scale like we said before. But you might be wondering, is there a way algebraically with some mathematical rules I could figure that out by just looking at this triangle? And yeah, you probably could, maybe like the law of cosines or something like that, but we very rarely do that. Instead, we'll learn a different method when we'll develop what are called components of vectors at a later date. So don't worry about trying to like get some trigonometric rule for every single vector thing. That's typically not how we do things. When you get right triangles, a lot of times you can just simply use the right triangle math to get things, which is fine. But here we'll invent a new method that has to do with what are called components in another video. But I wanted to show you how things can change a little bit as you change the direction of these vectors. All right, now that we've got some experience with scalar multiplication and vector addition, I'd like to see if you can invent on your own what's called vector subtraction. We'll start with the same two vectors, vector A with magnitude 3 pointing to the right, and vector B with magnitude 1 also pointing to the right. What does it mean to subtract vector B from vector A? Try to draw it out first and see if you can invent what subtraction is all about. Don't worry if you can't, but I always like to pose this question because I think you can, so try it. All right, well, it turns out that A minus B over here in symbols, vector A minus vector B, that's the same thing as just vector A plus a negative vector B. And what the meaning of this minus sign does when you put it out in front of a vector is it flips it 180 degrees. So we'll write that out. Flips the vector 180 degrees. It turns it all the way around, pointing in the other direction. So what we can do here is do that, and we'll erase b as it stands here, and then we'll just turn that into minus b. So I'll go ahead and put a minus sign on the end of it, and then flip its direction around like this. Cool. Now it still has a magnitude or a size of 1, so we don't put a minus sign out in front of that number. Again, that's the magnitude. It doesn't have any direction associated with it, but now we've changed direction. Cool. So what do we do now? Well, we just follow the rules of vector addition, which we already know. So we'll come over here. We'll draw our first vector, vector A. Oops. Use the same color here. Vector A. Actually, let me just erase. I don't like that other line under there. There we go. Vector A. Perfect. And then add to that. So we take the tail of B, which is here, and we put that, superimpose that onto the tip of A, which is right there. So we kind of have to draw this a little bit above, or else the lines are just going to go one on top of the other. So I'll draw it a little bit above. Okay, like that. And there's minus B, and let me change this length just a little bit longer to make it consistent. All right, now it looks like it'll work. All right, so we have A plus minus B, and now we go from where we started to where we finished, right there. So again, I'll label that. You don't always have to label start and finish like this. I'm just doing it now for clarity. So there we have it. And then you would measure that out, and hopefully you can see that that is equal to a length of 2. All right, so I've drawn it out over here at the bottom. You typically don't do something like this, but it's instructive, I guess. So the resultant vector R is now being shown to be vector A plus A minus vector B, where we flipped vector B 180 degrees, and you can kind of see how that's turning into, hopefully, this vector here. So we get a final magnitude of 2. Now again, watch out. We're seeing, hey look, 3 minus 1 is equal to 2. That certainly makes sense from regular addition, and it's working out fine here in one-dimensional vector subtraction. But if we were to try to subtract vectors in 2 dimensions, like we have just seen before with vector addition in 2 dimensions, you cannot just add or subtract the magnitudes, but it does end up working here in 1 dimension. Great. Okay, so we'll end the video there. We've outlined the 3 major mathematical properties we're going to need for working with vectors. We talked a little bit about 2 dimensions. We know to watch out for this idea of magnitudes and adding and subtracting when you're in 2 dimensions. And hopefully you get the sense as well about how scalars are different than vectors. All right, so take care and see you next time.